Yung recording pala ng mga to is ipopost ko sa Oble. So you can check it out later. Okay? Sige, I will summarize everything that we've discussed so far. First topic that we've discussed is indicial notation. Okay? So, pag sinabing indicial notation, we are trying to it is a notation that primarily shortens a set of equation, no? Sets of equation. And in doing so, we can concisely and efficiently write equations regarding solid mechanics. The second topic, we discussed tensors, and we define that tensors are mathematical objects that obeys some transformation laws. Okay? And we noted that vector and scalars are part of this, in a general sense, they are tensors. Okay? And the next thing that we discuss is stress. So we define stress as a second order tensor. Yeah. And we discuss about transforms, how to get how to get the how to get the principal stress and their corresponding principal directions. Okay? So ayan. And then strains, redefined. I will say redefined strains by first discussing two descriptions of motion, which is the uh, Lagrangian and the Eulerian descriptions of motion. And we concluded in our discussion that it is efficient or advantageous for us to use the Lagrangian description in solid mechanics, and for fluid mechanics, it's better to use Eulerian or the control volume concept, right? And then lastly, ito na. So in this last topic, we will discuss the relationship, okay? The relationship of stress and strains. Okay, of course, if you apply some stress to a material, it will definitely have strains. So we will try to connect those two using the constitutive equation. So one of the constitutive equation that you have discussed in ES102 is the Hooke's law. Okay, and that's what we're going to redefine in this session, primarily because we will limit ourselves to just defining elastic deformation. Okay, when we say elastic deformation, we are in the domain in which the material, if you let go or if you release all the stress, then it will go back to its original deformation. Of course, in real life, especially for a very large set of forces, if you apply it to your structure, for example, everything will it will most likely most likely behave in a non-linear and in a plastic way, di na elastic, okay? Inelastic way. But the knowledge of this elastic deformation is essential in understanding more of this advanced topic. So if you want to explore more of this, um, of course, uh, you you may explore this. Siguro mamimit nyo na siya if you go to your design courses. Probably you will touch a little bit of inelastic deformation. Even in this course pala, we will touch a little bit of inelastic deformation. And if you pursue your graduate studies, you'll definitely encounter all of this. But again, we will focus ourselves in understanding the elastic constitutive equation. Okay, so let's start. Any questions pala? Before I proceed with this, kung saan kayo nahihirapan. Anyway, siguro if you have questions, we can discuss those things later. Kasi what I plan to do in this session is also discuss to you um, your formative assessment. So lahat ng questions siguro mamaya we will have a forum where you can ask me. Then ask this group of students here. Okay, your classmates. Okay, so let's start. Yeah, so our objective for today is to discuss linear elastic solid, um, elasticity tensor, and isotropic materials. Okay, so here are some assumptions. First is the relationship between the applied loading and deformation is linear. Okay, so wait lang. So here you might remember the stress strain. So this is the strain and this is the stress, right? And you might remember this one, stress strain relationship. So here we have at this point from 0 to here at this point we experience an elastic deformation. Okay. Sandali lang class, wait lang. Sorry about that. Okay, so let's go back. Here we experience elastic behavior. Okay, and it's linear. Okay, this is the elastic region, and here we start to yield. Okay, so here we have no increase in stress, but we still elongate. We still experience strain. So this is the yielding region. Here we start to see that the material exhibits hardening. Okay, so it hardens and until it reaches an ultimate stress and starts to neck. Okay, and starts to neck and reduce its area, cross-sectional area. Okay, so I hope you still remember this stress strain curve. And for this class, as I've said, we will focus on this part, this elastic region part. And as you can see, the relationship between the applied loading or the applied stress and the deformation, you can think of it as the strain, is linear. Okay, next, the rate. The rate of load application does not have an effect. So what does this say? That your force is not impulsive. Okay. So ano ba yung effect ng impulsiveness? So for example, may and we will call this static loading. Ano ba yung static loading na sinasabi natin? Or quasi-static. May mga terms na ganun. When we say static or quasi-static, dahan-dahan lang yung pag-apply mo ng load as not to put an impulse, okay, to the structure. Okay, because if you have impulse, have you will add some, you will trigger, no, that the you will add some acceleration, thus dynamic na yung loading mo. Okay, if you have acceleration, then dynamic. As opposed to pagdahan-dahan yung pag-apply mo ng load, okay, pagdahan-dahan yung pag-apply mo ng load, the load application does not have an effect, or there's no acceleration, thus the loading is static. So yun yung isang assumption natin when we study statics. Okay? Now again, you can explore this at your higher CE courses. For now, we will not consider dynamic loading. Okay, upon removal of loading, the deformation disappears completely. And that is the description of this elastic region. Then it will go back to its original deformation. And lastly, the deformations are very small, or this will trigger the effect of the small strain assumption, or this is the small strain assumption. There is, for example, kasi, just to cite an example, no, para maintindihan niya. For example, I have this column, okay? I have this column or something. Now I apply some loading here, okay? And some loading here. Okay. Now, if it deforms and the deformation is so big, okay? Ano ba to? If it deforms and the deformation is so big, sabihin natin nag-curve ng ganyan. Okay? Curve ng ganyan. Still, you have these forces, okay? Meron pa din yung mga forces na yan. And you have this force. And as you can imagine, this thing right here, since this distance is so big, it will induce additional moment. So ito yung tinatawag nating P delta effect. Okay? And of course, we will not study this for now because we are just considering that this delta or this distance is very small. That is the moment that this force induces is negligible. Okay, so we will neglect first the P delta effect. But of course, yeah, in real structures, you will often see this one, especially if you have large set of forces like an earthquake. So ayan, kino-consider yung effect na yan. Okay? So we will assume those things are not happening for now. Still, if we just assume all these things to not happen, still this is very useful in understanding the behavior of a certain material, at least on the basic level. Okay, so here we have this initial notation equation. We note that K and L are dummy indices, tama, and I and J are free indices. So sigma ij is the Cauchy stress tensor. This is the same tensor that we have discussed in module 3. Epsilon KL is the infinitesimal strain tensor, the same strain tensor that we have discussed in the previous lecture. And we will try to get this elasticity tensor. Okay, we will try to get that. And this elasticity tensor is determines the relationship between these two tensors. Okay, naintindihan yung assumptions, kung bakit may assumptions na ganyan? Yes? And yes. Okay. Sige. Let's move on to the next So as you can imagine, if we have a 3D case, okay, we have a 3D case, then CIJKL, it has 4, okay, it has 4 indices, it has 81 elements. Okay, tama? 3 to the 4, 81 elements. Since, ayan, ano itong ibig sabihin nito? Epsilon KL is equal to epsilon LK. It just means that we have we have a symmetric strain tensor. Tama? Symmetric yung strain tensor natin. Thus, it will reduce to 54 elements. Okay? 54 elements. And since sigma ij and sigma ji is equal, okay, or the stress tensor is symmetric, then this will be reduced to 36 elements. Okay tayo dito. Sige. Now, we can define this CIJKL, okay, using just 36 elements. So if we're going to, still, CIJKL still has 81 elements, no? But since mostly naman sa kanila ay equal, then we can just represent it into 36 elements. And thus, if I put this into a matrix, I can just make it a 6 by 6 matrix. Okay, you can think of it that way. Now let's define. Okay, let's define what CIJKL means. Okay. Now we can define CIJKL using this set of equation. So here we have the lambda, mu, and kappa. Okay, we call these Lamis coefficients. Okay, Lamis coefficients. So here we have the lambda is a coefficient to 2 Kronecker delta, which is multiplied. Here, the sum of the 2 multiplied Kronecker delta and the difference of 2 multiplied Kronecker delta. And we hope that using this form, okay, so this is just the form that is proposed by Lame, okay? This is just a form. So we hope that using this form, we can define systematically what the elements of this elasticity tensor are. Okay. Since the strain tensor is symmetric, we still have discussed this. CIJKL is thus CIJLK. And here, sigma ij, ji. So CIJKL is equal to CJIKL. Okay. So nirepeat lang yung symmetric assumption on those two tensors. Therefore, this one will become like this. Okay, anong nangyari? So yung kappa nawala, no? Yung kappa nawala kasi ito nga, no? Yung IKJL, yung ILJK is just equal to IKJL. So this will be cancelled. And this one is the same, so na-multiply by 2. Okay? If you add them, it's 2 mu delta IK delta JL. This one stays the same. Okay? Naintindihan yung nangyari dito? Yes? Please click yes, guys. Yeah. Okay, sige. Yeah. Next. So here, what happens? So we have this relationship, right? Now we plug in the form that we are proposing is for elasticity tensor. So this elasticity tensor is just this one. Okay? Yan. So we just plug it in and we multiply. Sorry, nagkamali. Dapat subscript ito, no? Malaki yung... Dapat subscript yan. Anyway, so we just distribute. Okay? We just distribute this here. Okay? Then here. And then we produce this equation. And then, what happens? So na-repeat lang siya. And then next is that we define epsilon, we substitute, okay? We substitute when k is equal to L. Okay? What would happen if k is equal to L? So this one is kk. And then, so this one becomes 1. May question tayo. Sir, if 36 independent elements, so may tanong, ay sir, nakalimutan ko pong i-ask, if 36 independent elements, then 36 times 2 is 72. Kung symmetric ano, hindi po ba independent din yung diagonal elements? So plus 9 elements. Sige, balik tayo dun sa discussion. Wait lang So, 81 elements. Nagsimula tayo sa 81 elements. 81. Ngayon, kung symmetric yung KL and then LK, magiging minus minus 27. No? Bakit 27? Kasi it will now be 3 to the 3. Okay? Magiging 3 cube na. So magiging 27. Dali. So instead of 3 to the 4, since yung isang element mo is equal naman dun sa isang index mo, right? So magiging 3 to the 3 na lang. Thus, mawawala yung 3 to the 3, 27, na elements since equal naman yung 27 na ito dun sa ibang elements. So thus, magiging 81 minus 54. 81 magiging 54. So 81 minus 27 equals 54. Next, in this 54 independent elements, kapag yung isang index mo is equal, doon sa iba pang elements mo, ilan dito sa 54 elements mo yung equal kapag ij equals ji? 18. Saan nakuha yung 18? Okay? So, saan nga ba nakuha yung 18? Let me think. Kalimutan ko na rin eh. Na-solve ko to nahirapan din ako dito sa problem na to in thinking about this. Pero brute force ko ata ito in order to derive this. So sinulat ko lahat yung 81 elements and then ang ginawa ko is you might want to try this. I'm sure this is not the way to think about it properly. And I'm sorry about that kung nakalimutan ko yung how to derive it. Pero ang ginawa ko dito is, after this one, intuitive ko itong naisip eh. Yung 3 to the 3, 27. Parehas dun sa 27 elements ng 81 elements. So, na-minus ko sila. But after this, nahirapan ako isipin. Ang ginawa ko na lang, brute force ko, sinulat ko yung 54 elements, and then, I assume ij equals ji. And lumabas na 36 yung independent elements ko. Kailangan kong mag-minus ng 18. I'll get back to you on this, okay? Pero you might also want to try to brute force it. Madali lang naman i-brute force. Okay? Sige, balikan kita dito on this question. Okay? Pero the first time that I solved this, I did brute force to get the independent elements. Okay, sige. Sige. Thank you for the question too. Para na-clarify din sa mga classmates. Okay? Ngayon, so let's go back to our discussion. So, sigma ij, no? And we have defined this one equation. Now, what happens if k equals L? Okay, in the case where k equals L, we'll see why I do this later. Okay, so if k equals L, yan, so palitan ko ng k equal yung L ng k, yan. So if this one is delta kk, then this one is equal to 1. Okay? So, since parehas na, yun yung definition natin ng Kronecker delta. Since parehas na. Thus, yan, nawala siya dito sa susunod na equation. Same with this one. What happened in this one? Sigma, okay, sigma ik. Sige, palitan natin yung L ng k. Sigma. Ano sigma ng sigma? Delta JL. What happened? So, yung L na palitan ng K, okay? Delta IK KJ. Okay? So, if yan napalitan ng K, then we apply this one, lahat daw ng I mapapalitan ng lahat daw ng I mapapalitan ng K. Okay, so what happened here? Wait lang. Lahat daw ng K mapapalitan ng I. So this became epsilon I. Okay? K siya doon, naging I dito. Ngayon, lahat daw ng L, sorry. Di pala. Let's repeat. Here, lahat daw ng I, lahat daw ng K mapapalitan ng I. So yan, yung nangyayari. Lahat daw ng L, okay, mapapalitan ng J. So yan yung nangyayari. Here, na-operate lang pala dito yung Kronecker delta. So here, ang nangyari is that yung K, okay, lahat ng L mapapalitan ng K. So, yung L dito, napalitan ng K dito. So, inoperate lang pala yung delta. Okay? Next is here. So, balik tayo dito sa equation. So, kopyahin natin yung equation na yan. Then we go back here. And we solve for epsilon ij. So solving for epsilon ij, 1 over 2 mu equals sigma ij, lambda delta ij, epsilon kk. And if we solve this one, okay, so here palitan natin, we look for the case where where I equals j. Okay, yung case muna na yun. We have this thing, okay? This thing right here. So epsilon I equals this. And saan daw galing yung 3? Okay, saan daw nang galing yung 3? So, tingnan natin. 1 over 2 mu sigma ij minus delta ij epsilon kk. Wait lang. Saan ba galing yan? So here, palitan natin lahat ng I ng j. Lahat ng j ng I. So if this is I, okay, if this is I, then maganda siguro na I write sa aking whiteboard. Share. So epsilon ij is equal to 1 over 2 mu delta ij minus lambda delta ij epsilon kk. So here palitan natin lahat ng j ng I, sigma I, okay, minus delta I epsilon kk. Okay. So here, epsilon I 1 over 2 mu sigma I minus since this one is lambda and this one will become 3. So dito nang galing yung 3. Epsilon kk. But since this is another term, okay, since this is another term, we have the freedom to change it into II. Okay? Since that is another term. Para maging consistent dito sa ating equation. Okay? We can do that because yun nga, it's another term and gusto natin consistent na I yung yung index natin for epsilon. Okay, now rearranging, yun na yung nangyari. Kaya na magsulat. Is equal to 1 over epsilon I plus ayaw magsulat ng pen ko. Ayaw magsulat ng pen ko. Sorry class ha. Pero gets nyo naman, after this, what will happen is, ayaw magsulat, is that epsilon II is equal to, ayaw magsulat ng pen ko. Sorry. But after that, what will happen is makukuha na natin yung equation na to. Okay? Ayan. And of course, if you try, so meron tayong epsilon II, papalitan natin yung epsilon lahat ng I ng K. Okay? Para kung sinubstitute natin ito dito, we can get this term. Okay? So saan ang galing ito? We just copied this. Di po ba yung Kronecker delta I1 and 2 yung possible value? No. Kinorek ko na yun doon sa ating module. Yung Kronecker delta is equal to 1 if, okay, it's equal to 1 if both indices are, we call this, both indices are equal, and 0 if the indices are not equal. In this case, since ang nangyari, ginawa natin tong delta II, diba? Diniscuss natin yung dati, na yung delta II, since dummy index na yon, so pag dummy index, you expand it into 3 terms. So magiging, since parehas yung terms, 1 plus 1 plus 1, so magiging 3. Gets ba? Ito class. Diba naging delta II? Delta II. Yan, okay. Sige, ulitin ko lang. Delta II, magiging, since parehas na siya, dummy index, so magiging 3. Kasi 1 plus 1 plus 1. Ayan. Okay. Sige, thank you for the clarification. Next, we substitute this thing here. Pero ang gagawin natin, palitan lang natin ng K, yung I. Okay? So yun yung nangyari dito. Sigma KK na. Okay? Next. So meron na tayong this equation. Okay, na-derive na natin. Ayan. And this is the form of the Hooke's law in individual notation. Okay? Pero since what we're getting in experiments, ayan. So in experiments, what they got is E, okay, is E, which is the modulus of elasticity, and nu, which is the Poisson's ratio. So ano yung modulus of elasticity? That is the slope. Okay, so balik tayo doon sa stress strain curve, pero hanggang sa linear lang tayo. That is the slope, okay, of the elastic part or the linear proportional part of the stress strain curve. So that is the E. Okay, or the modulus of elasticity, also known as the Young's modulus. Okay, ano yung nu? Nu, discuss naman to, no? Pero I'll just repeat the concept of the Poisson's ratio. So the Poisson's ratio tells you the proportion on which the material changes its length in the perpendicular direction, okay, in the perpendicular direction of which the force or the stress is applied. So for example, Example, I hope this would work. Ayan, nag-work. Okay, so for example, I have this thing. If I pull this with a force, two things would happen. Okay, two things would happen. Well, it will be like this. Okay. Ito yung original na shape niya. Okay, that's the original shape. So two things happen. First, it elongates. Okay, it elongates. So it elongates and it thinned, right? Pumayat siya. And this is that one, the nu. Okay? So nu is a coefficient or a proportional factor on which states how the object deformed in the perpendicular direction to the force. Okay, so for example, in steel, we have a Poisson's ratio of 0.3. So, ibig sabihin, kapag hinila mo daw yung steel bar, yung length na ipapayat niya is 0.3 ng deformation niya longitudinally. Okay? So, yun lang yung concept ng Poisson's ratio. Okay. Now, those values are connected to the Lames coefficient. So, yung Lames coefficient, hindi na natin masyadong ginagamit, no? So, ito na lang yung ginagamit natin. And it's connected to, it's equal to these values. Okay. You might remember again, this one. Ano to? G, tama, no? So, that is the G, or the shear modulus, or the modulus of rigidity. So, nang ba yun? Of course, if you try to experiment, this is the tau, okay? This is the tau, and this is the delta, no? Sorry, the delta. Rather, it is the phi. Mali. The phi. Gamma. Sorry. Gamma. Or the shear, engineering shear strain. The slope is G. Okay, so equal ito dito sa Lames coefficient mu. And now, if you substitute all of these things to this one, then we get this equation. Okay? Ayan. And, okay, how to expand this? How do you expand this? So noting again that ij are free indices and kk is a, kung ang mu po ig, ano po ulit yung lambda? Ang lambda is this one. It's related to this one. Okay? I do not know what historically kasi, no? Historically, si Lames, yung nag-propose ng Lames coefficient, pinopose yung form ng Lame. And then by experiments, it was ito na lang yung ginamit. It was found out that it is related to this one. Because ito naman yung talagang mini-measure in experiments. Okay? Ayan. Anyway, this form is what we're going to use. Okay? And if we expand this, then we get the Fuchs law that you studied in your ES 102. I hope you studied this, no? And it's very intuitive. Intuitive naman, no? Strain at 1, 1 is equal to 1 over E sigma 1, 1. Pero if you account the Poisson's ratio, then the direction, the deformation or the material will deform at the axis 2, 2 and axis 3, 3. Okay, same with this one. Or reduce its length. Okay, now sigma 2, 3, wala nang sigma, wala nang, wala na tong term na to kasi hindi parehas yung I and J. Okay, so this defines the shear strain, the infinitesimal shear strain. Yan lang. Naulit. Pinagkaiba. Sorry. Yeah, that's it. And of course, ito yung kanina nating na-discuss, no? If you substitute everything, you sig delta ij, if you solve for sigma ij, then you will get this form. You will get this form. Ito naman baliktad, no? Ang isolated ay sigma ij in terms of epsilon ij. So recap of today's class. First, we discussed the necessary assumptions in deriving the linear elastic solid. So the constitutive equation for the linear elastic solid. We discussed the elasticity tensor and we derive the Hooke's law. Yeah, so congrats. We just finished the the continuum mechanics part, right, of CEAT. Any questions? No? Medyo math part yung ano, no, yung derivations, and it really challenges if you understood yung past modules, especially yung indicial notation, because manipulating indicial notations requires some. Okay, sige. You can ask. Because manipulating indicial notation is different from your ordinary mathematical notation. Okay. Now, I want to discuss or find your insights, okay, on our FA. Sino na naka-start ng formative assessment 1? Hi guys, sino na naka-start nung FA1? Please click yes na lang kung no. Okay. So here siguro with the remaining parts of the remaining time for our synchronous meeting, I want you to